Hello everybody. In this video, I'm going to talk about Doppler effect in special relativity. What is Doppler effect? Doppler effect is the observed change in frequency or wavelength of a wave due to the motion of either the source or the observer, or both the source and the observer. All waves can undergo Doppler effect, but we are generally interested in Doppler effect in sound and Doppler effect in light. While the Doppler effect in sound does not come under the category of relativistic Doppler effect, the Doppler effect in light is what is called as the relativistic Doppler effect. So this video is primarily going to focus on Doppler effect in special relativity, or the relativistic Doppler effect, which is the Doppler effect that a light wave suffers from. Now first let's deal with the sound, the case of the sound. We know that sound requires a material medium for propagation. Therefore, in the case of sound, if the source or the observer, or both the source and the observer move, then there is going to be a change in the observed frequency of that particular sound wave. We are all too familiar with the, for example, the horn blown by a train, for example, approaching train while we are standing on the platform, on the railway platform. We know that when the train approaches us, we hear the pitch of the sound increasing as it approaches us. That is, the sound becomes somewhat unbearable because of the higher pitch of the horn blown by the train. On the other hand, when the train is leaving the station and while we are still standing on the platform, we would find that this sound goes to lower frequencies, and it kinds of gives a melancholic feeling, right? There we say that the horn blown by the train goes to lower pitch. Now higher pitch and lower pitch, by higher pitch and lower pitch we mean higher frequency and lower frequency. So this is all too familiar to us. Even while we stand on the for example on the road, on the side of the road, we see ambulances passing by. Observe that an ambulance that approaches us produces sound of higher pitch, whereas while it recedes away from us, the pitch of the sound decreases, it becomes more bearable. So generally for humans, higher pitch sound becomes somewhat unbearable, and for most people lower pitch sound is bearable. Now this effect is all too familiar for us. This is the Doppler effect in sound. Before we proceed to discuss Doppler effect in sound and light, let us try to get a general understanding of what happens in Doppler effect. Suppose we have a source of wave. Now waves are emitted from the source in all directions like this, and let us say there is an observer at some distance from the wave, and let us consider the source to be stationary initially and the observer to be, let us say, moving towards the source with a velocity, let us say, v. Now the waves are consecutively emitted by the source, and as each wave progresses towards the observer starts counting the waves, let us say. Now the time duration between these two waves is the time period of the wave, and number of such waves counted by the observer per second becomes the frequency then. So if the observer moves towards the source, he will be able to meet more number of waves in less time compared to the number of waves emitted by the source in the same time, and therefore he will count more waves. That means he will find that the frequency, let us call that frequency as nu, that is observed by him, seems to increase for him. And if the source frequency is actually nu naught, in this particular case when the observer is approaching the source, one can have a general understanding that the frequency nu observed by the observer will be greater than the actual frequency of the source. Now this is true for both sound waves as well as the light waves. On the other hand, if the observer starts, let us say, going away from the source, let us say he is running away from the source, what he would find? He would find that for the same time, he would find that he is counting less number of waves, because he is moving now in the opposite direction with the same velocity v, and in this particular case he would find that nu, that is observed frequency, to be less than the actual frequency emitted by the source, which is nu naught here. So that's how we can get a general understanding of how one would get a frequency increase if the source and observer are approaching each other, and one would get a frequency reduction if the source and observer are receding from each other. Now let us proceed to deal with the Doppler effect in sound and light. We will first discuss Doppler effect in sound, and then we will go on to discuss Doppler effect in light, which is relativistic Doppler effect, in some detail. In sound, so in the case of Doppler effect in sound, we can write an expression for the observed frequency is equal to the actual frequency emitted by the source multiplied by 1 plus, let's say, small v over c, 1 minus capital V over c, where nu is the observed frequency, nu naught is the actual frequency of the source of sound, small v is the velocity of the source in the medium, capital V is the velocity of the observer in the medium, and small c is the speed of sound in the medium. Now, simply because sound requires a material medium for propagation, here individual velocities of both the source and the observer are important. That is, if the source moves, you would get one value for the observed frequency. If the observer moves, you will get one value, another value for frequency. And if both of them move, you will get a different value for the frequency. So the individual motion of the source, the observer, and the relative motion as well, all the three are important in the case of sound, because sound requires a material medium for propagation. Now in this particular sign here, the small v can become positive if the source is approaching towards the observer, and it becomes negative if it is receding. The same way here, v is positive, capital V is positive if the source is approaching, if the observer is approaching, and v becomes negative if the observer is receding from the source. So this is one simple expression for finding the Doppler effect in sound. But there is no relativistic idea here, so it is not a relativistic case. It is a general case of Doppler effect that is applicable to sound. But in the case of light, light does not require a material medium for propagation. Light can travel in vacuum, and the Doppler effect for light is relativistic in nature, because the individual motion of the source and the observer are not separate in light. The relative motion is important in Doppler effect for light. Now let us proceed to discuss Doppler effect in light, also called as the relativistic Doppler effect. Let us proceed to discuss Doppler effect in light, also called as relativistic Doppler effect. For Doppler effect in light, three cases are possible, namely transverse Doppler effect, longitudinal Doppler effect for approach, and longitudinal Doppler effect for recession. What is this approach and recession? First we will deal with transverse Doppler effect. What do we mean by transverse Doppler effect? Transverse indicates that the direction of motion of either the source or the observer, or both, they are in perpendicular direction. That is, if the source and observer are connected by a line, then the motion of the observer could be in a direction perpendicular to it, or the source could be moving in a direction perpendicular to this line. Transverse indicates the perpendicular direction of motion of either the source or the observer, or both, with respect to the line connecting the source and the observer. This is called transverse Doppler effect. Now the source of light is emitting rays and the observer is moving with a velocity, let us say v, in a direction perpendicular to the source. Now in this situation, let us say that a certain number of waves are emitted by this particular source for a given time, and that certain number of waves, let us call that as frequency of the source of this light wave. So we say it is, let us call that as nu naught, which is the actual frequency of the source. If the time duration between two successive waves emitted by such a source is, let us call that as t naught, then we know that the frequency and this time period are inversely connected. So we can say that t naught is equal to 1 over nu naught. Right? Now the observer is going to observe this wave emitted by the source, and if he is moving in a perpendicular direction, what happens to him? Because of special relativity, when the observer is moving with respect to the source, that any time measured by the observer must be dilated. So the relativistic idea of time dilation comes into the picture here. For those of you who are not familiar with the concept of time dilation, please do check out my video on time dilation in special relativity. And therefore, the time observed by this observer, let us call that as t, is a dilated time, and that time must be equal to t naught over 1 minus v squared over c squared within square root. Now this is the time that he measures for two successive waves, and therefore obviously it is understood that this time must be reciprocal of the frequency that is observed by this particular observer. Now how these two are connected is the question. So connecting these expressions, we can straight away write this t as 1 over nu and this t naught as 1 over nu naught. So I will write 1 over nu naught times square root of 1 minus v squared over c squared, and therefore taking reciprocals we get the Doppler effect directly, the expression for Doppler effect directly, that is nu is equal to nu naught times 1 minus v squared over c squared within a square root. So this is the expression for the transverse Doppler effect in special relativity. Right, so this is the expression for transverse Doppler effect. Here we can clearly see that the observed frequency is going to be always less than the actual frequency, simply because this factor square root, this factor square root of 1 minus v squared over c squared is always going to be less than 1, because that is v is always going to be less than c. So simply because v is less than c, this particular term is always going to be less than 1, and therefore we can conclude that nu is always lower than nu naught. So in transverse Doppler effect, always it is going to be observed frequency less than the actual frequency. Now there are two other cases that are possible. First one is longitudinal Doppler effect, where the observer is approaching the source and the second one is longitudinal Doppler effect, where the observer can go away from the source. In both the cases it is longitudinal because the direction of motion of either the observer or the source is parallel to the direction of the line joining the source to the observer. So let us proceed to discuss these two cases now. Okay, so for the case of longitudinal Doppler effect approach, the observer is going towards the source, let us say. Equivalently, one can assume that the observer is at rest and the source is moving towards the observer. In either case, the equations are going to be the same. Right, in this particular case, what happens? In any given time t, because of the motion of the observer, let us say, towards the source, in a time, let us say t, the distance traveled by the observer is going to be v times t, is the distance that the observer travels in the same duration of time t, which is the duration between two successive waves that is emitted by the source. So here the actual frequency for this observer is going to depend on another time, let us say capital T, which is 1 over nu here. Now in that time t, capital T, that is going to be less than this time by a factor Vt over c, because c is the velocity of the light that is emitted by this particular source. So the time t that this guy measures, observer measures, is going to be t minus Vt by c, because Vt is the distance and Vt, distance over velocity, is time again. So this is an expression for approach. Why it is minus here? Because he is going now, the distance between the source and the observer is reducing by a factor Vt, and therefore the time also has to proportionately reduce. So it is Vt over c is the time by which the actual time t is going to come down. Now this time can be taken out, and therefore you are left with a 1 minus v over c factor, and therefore now you can equivalently convert these time durations or time periods into equivalent frequencies. So this capital T is the time period between two successive waves encountered by the observer. So that is going to be 1 over the frequency, which is the observed frequency, and that is equal to this time t is going to be dilated time for him, because he is in motion, he is in relativistic motion with respect to the source. So you have to use the relativistic idea of time dilation again, and therefore I write t naught over square root of 1 minus v squared over c squared, and then you have 1 minus v over c factor remaining here, right? So one can go ahead and continue the equations here, because this t naught is again going to be equal to 1 over nu naught. So if I write 1 over nu is equal to 1 over nu naught square root of 1 minus v squared over c squared, and I have what in the numerator? I have 1 minus v over c in the numerator. Now I can do some modifications here. So 1 over nu is equal to 1 minus v over c nu naught. I can write this as square root of 1 minus v over c, another square root of 1 plus v over c, right? This, and numerator I can write this as square root of 1 minus v over c, another square root of 1 minus v over c, right? So this is how I can rewrite this expression here, and therefore now I say that this minus and this one will cancel, and the remaining terms are going to be the expression there, which again we can write down as 1 over nu as equal to square root of 1 minus v over c nu naught square root of 1 plus v over c. Please bear in mind that these symbols are for v and these are for nu. And now if you write nu, which is the observed frequency for this particular observer, that is going to be nu naught times the square root of 1 plus v over c, because this goes to now numerator while I take the reciprocal of this, and therefore the denominator is now going to have a negative sign. And this is the expression for relativistic Doppler effect when the source and observer are in a relative motion approaching each other. So we can conclude that this expression is the final expression that we need, and we can verify that when the source and the observer approach each other, or one of them approaches the other, the frequency has to increase. And here you can see that the numerator has a term that is greater than the denominator, so the square root term entirely is going to be greater than 1, and therefore when you multiply a number that is greater than 1 with the original number, your resulting number is going to be greater than the original number. Therefore we can conclude that nu in this case is always going to be greater than nu naught, because of course obviously the source and the observer are approaching each other. Let us proceed to discuss the third case, which is the longitudinal Doppler effect for recession. Recession is either of them or both going away from each other. Right, so now we are discussing the third case, that is the longitudinal Doppler effect for recession. A recession happens when either the source or the observer move away from each other, or both of course relatively move away from each other. In this case the distance Vt is still a factor, but here it is going the opposite direction. That means the observer, as he goes away from the source, is going to take a longer time to count the same number of waves. That means of course the distance between the source and the observer increases. That will take more time for the waves to reach him, and therefore this expression that we wrote for longitudinal Doppler effect is still valid, only the sign is going to be now different. Therefore here the time duration that the observer counts, t, is going to be equal to the actual time t plus an extra time Vt over c, where Vt is the extra distance traveled by the observer in that particular time t, and therefore here you have capital T is equal to small t times 1 plus V over c. And again the same things are holding here also valid, that is your t is equal to 1 over the observed frequency, and this t is the dilation that occurs because of relative motion between the source and the observer, time dilation of special relativity, and that factor is going to be equal to t naught over square root of 1 minus v squared over c squared, and therefore you have this term here in the numerator 1 plus v over c. And then I can extend it on this side, continue to write this out. So I will say that it is 1 over nu, which is the inverse of the time period or reciprocal of the time period, and here this t naught is going to be a reciprocal of the frequency nu naught, and this factor 1 minus v squared over c squared still remains, and the numerator becomes 1 plus v over c. And therefore when we take a reciprocal and do the simplification just like how we did for the approach case, we will end up with an equation where nu is equal to nu naught square root of 1 minus v over c 1 plus v over c. So I have skipped one step here. Again I will write this as square root of 1 plus v over c multiplied by square root of 1 minus v over c, in the numerator 1 plus v plus c square root multiplied by square root of again 1 plus v plus c. The plus and this numerator plus will cancel, so when you revert it you will get 1 minus v on the numerator and this as the denominator. Now this is the final expression for Doppler effect for the longitudinal case when the source or the observer or both recede away from each other. Here you can clearly see that this factor in the numerator within the square root is going to be less than the denominator factor, and therefore the whole square root term is going to be less than 1, and therefore when you multiply a number by a fraction, this number as a whole is going to be less than this, and therefore you are going to have here in this case nu less than nu naught. That is, the observed frequency is going to be less than the actual frequency of the source, because the source and the observer are going away from each other. So the intuitive feeling that you have now less number of waves to count is clearly brought out by this expression for Doppler effect for the longitudinal case of recession between the source and the observer. So that in total completes our discussion of transverse and longitudinal Doppler effect. But that is not all. What if the motion of either the source or the observer is at an angle with respect to the line connecting the source and the observer? Because we have discussed two very special cases, that is a transverse case where the angle is 90 degree between this line and the direction of motion, and the longitudinal case in which the angle is either 0 degree or 180 degree, depending on whether you are talking about the recession or approach. Now therefore we have to generalize this expression. The whole discussion has to be generalized, and we have to arrive at a very general expression for Doppler effect for light or relativistic Doppler effect, in which these three cases turn out to be special cases of that general expression. Let us do that.